Does it move orderly, or does it go wherever?
Yeah.
That's how electricity is. It will go wherever it's allowed. So it can move through your hand, it can move through this metal, it will move through every possible path. So we need to also, with insulators, we need to be able to contain that, and we create a path for electricity through our conductors, but we don't want it to flow through this metal. So we have insulators, and we only allow it to flow and go into those lights, and turn on the lights, or turn on those receptacles wherever we want. So with our conductors, we create a path for electricity so that we can make electricity do some work for us. What kind of work does electricity do for us? What do you think? What kind of work does it do?
It gives us light.
It turns on the light, right? As soon as we allow current to flow through those conductors, it allows us to have light. It turns on a refrigerator, it turns on a microwave, it turns on a hairdryer, it turns on a fan, anything that we want. There are a lot of devices that we use for electricity, but we create a path for it, even through an extension cord. So we go ahead and we plug it in here, and we create a path with an extension cord, and we take it to, I don't know, to a tool that we're gonna use outside, right? Or a power washer that we're gonna use to clean your driveway. We connect that extension cord, and we create a path, and we take it to the load that we wanna connect to it, and that is what we do with wires. This is what we do with all of the wires that we run around our homes. We create a path for them, and our conductors usually run together. So the two conductors that are going to be creating that loop will run together, and they will connect to the load, and one of them will be the path that will come back to the panel and close that circle, okay? So our conductors actually have to travel together and create that path. Now, in order to be able to study a circuit, there should be something working in the circuit. For example, I cannot measure voltage if the circuit is not on. The voltage actually has to be flowing so that I can measure. The amps actually have to be flowing so that I can measure. So a load has to be on so that I can measure what is the amperage that's flowing and what is the voltage. So we have our voltage, our current, and our resistance, and we have our power. And in order to measure it, we use Ohm's law. Ohm's law, we said yesterday that it is the relationship between our current, voltage, resistance, and we can also measure our power consumption. So Ohm's law tells us that if I want to get voltage, what do I need to do?
Carbon by
Multiply.
Resistance by current.
Right?
Yeah.
Current times resistance. If I want to get current,
What is resist?
now this right here is just one formula that I can use to be able to get this. We actually have 3 formulas for power, 3 formulas for resistance, 3 formulas for voltage, and 3 formulas for current. But this is just the simplest formulas that we can use. So if we wanted to get resistance, what do we do?
Voltage
It's voltage
by current.
divided by,
Divided by
Current.
current, right? And that power wheel is what I gave you guys yesterday, which are all of the formulas.
current times.
These two multiply, and this one is divided by current or divided by resistance, right? This is how this formula is used. So our voltage can be divided by current, or the voltage can be divided by resistance, and the amps and the resistance will multiply with each other. That's how this formula to use. Now, we have our second formula wheel that is very similar to this, which is our pi. And it tells us that if I wanted to solve for power, what do I need to do?
Multiply current by volt.
I take current and I multiply it by voltage, right? Now, how do I pick if I use this formula, or if I use this formula wheel, or if I use this formula wheel? How am I gonna know which one to use?
One is just if you trying to figure out the power usage.
It actually depends on what value you have. So if you don't have, let's say for example, you don't have resistance, but you have power and you have amps, you can get voltage, and then when you have these two, then you can get resistance, right? So you can go back and forth with these power wheels, and what you want is to solve for the value that you have, depending on the values that you have in hand. You wanna use the formula that works so that you can get other values, so that you can continue to solve for the circuit. So this formula tells me that if I want I, and I only have power and voltage, what do I need to do with them?
Power divided by
Power divide.
Power divided by voltage, right?
Voltage.
And if I wanted to have, or to solve for voltage, and I only have power in amps, what do I need to do?
power divided by
Power divide to
Power
the current.
divided by
Current.
and the current.
my current, right? So it all depends on what values I have. This is what I'm going to use, and this is how I'm going to pick what formula wheel I'm gonna use, right? And we're not gonna get into the other complicated formula wheels, because we can use the square root of voltage, we can use the square root of power, and we can go into other formulas, but you guys are gonna do that in mod 1. Not in this class, but in mod 1 we will go over all of those other formulas. Alright, so when we're using our Ohm's law, we have to understand that there are different ways that we can measure. So there are measuring tools that we use for these values. So the measure of voltage is the volt. The measure, it could be thousands of volts, which would be kV. It could be millions of volts, which would be a capital M and a V. It could be giga, or we can go down to low voltage, and it could be millivolts, which would be a lowercase m. It could be also micro, which would be like a weird U, and it'll be volts. It could be nano, which it would be an N. So there are different types of measuring for our voltage. The same thing will happen with current. So for current, it's the amp, the ampere. This is how we measure. And we have to have our loads on to be able to measure an ampere. So I can't measure an ampere if my load is not on. I have to have the circuit on and the load turned on so that I can take a measurement in voltage, because I said yesterday that our electricity is invisible. So unless there is a flow, then we can't use our measuring tools to be able to measure. Then we have our resistance. Is measured in ohms, in the symbol omega. This is the symbol that we use to be able to measure our resistance. And in our multimeters, that's what we're gonna have. We're gonna have our ohms, and the same thing. It might be kilo ohms, it might be milli ohms, it might be giga ohms. We have different measures, different sizes. So these prefixes are just to be able to abbreviate all of the zeros that we have, because we have high, high resistances, we have low resistances, we have high current, we have low current. So all of these are different measurements. And then we have our power that is measured in watts. So these are all our the different ways that we measure our circuits, and when we measure them with a multimeter. We have measuring tools that we can use to be able to measure a voltage, but our circuits have to be on in order to be able to take a measurement. And this is where safety as electrician comes, it's the first thing that we think about as electricians is our safety. What type of tools are we gonna use? All of our tools have to be insulated, and if you're gonna be working with live loads, now they have to be rated. Because most of our tools are insulated, but I'm gonna show you guys that they say, the tools that we have here in the class, even though they're insulated, they said that they're not for live circuits. So if you guys are actually gonna be working with live circuits, now you have to invest hundreds of dollars to buy tools that are actually rated for the voltage that you're gonna be using. Because there are some electricians, for example, linemen, they work with power, they can't shut off the power for the city when they're connecting, or when they're disconnecting, or when they're fixing something that's broken, or maybe when they're giving maintenance. They can't turn off the power. What they do is they use specialty tools, they use specialty gloves, they're trained how to be able to handle all the wires, how to be able to make themselves at the same potential like the system that they're working with, so that they don't close the circuit or they don't become part of the circuit, right? This is something that they train because they're working on live circuits. Now most of us, like for me, for example, 90% of the time we never worked with power. What we did is that we identified what was the circuit, we would turn it off at the panel, we would lock it, we would tag it, we would make sure that nobody turned on the power while I was working on it or somebody else was working on it. We would fix or we would troubleshoot whatever we needed to do, and then we would turn it back on, right?
Yeah.
But there are some instances, for example, when they would call us for a service call at 2 in the morning because there was a building that lost power and we needed to go check it because somebody was on, let's say that they were connected to a machine, and right now the generator was going to be working, but it was only gonna be working for a couple of hours, so we needed to work with live power. So we needed to take out our specialty gloves, we needed to take out our boots, we needed to make sure that we were safe and secure, because now we were gonna be working on live wires, right? So this is something that as electricians, safety has to be first. Depending on the environment that you're working in, you have to use the tools that are appropriate for the use. Okay, so we have different types of circuits or different types of current. So what type of current do we use with a battery?
DC.
Direct current, right? Which is known as DC. Because when we're using direct current, our current only goes in one direction. So our current only flows in one direction. This is DC current. When we have alternating current, our current actually, so for example, this is positive and this is negative. With alternating current, we'll have a positive alternation, a negative alternation, positive, negative, positive, negative, and this happens 60 times per second. And this is the type of current that we mostly use, alternating current. It has a positive alternation, it has a negative alternation, a positive alternation, negative, and a positive. This is happening because when we're generating our power, yesterday we were talking about how we generate power, right? We have a generator, and that generator is alternating back and forth, going into the positive and to the negative. So as the generators in our substation are alternating the current, all of our electrical systems are alternating, so they're going back and forth, 60 times per second. Now, these alternations, 60 times per second, are in certain parts of the world. There are some parts of the world that actually alternate 50 times per second. But here in the United States, because we were later on into installing our system, before we went into the 50 alternations per second, we found a much more efficient way, so we were able to do the 60 times per second alternation. And this is why this is the system that we use here in the United States. And this is the difference between DC current and AC current. Now our batteries, they have polarity, right? A battery has polarity. So our battery will allow current to flow only in one direction, and it'll start using up all of the pressure. And when the battery, if it's not rechargeable, is done with the pressure that it applies to the circuit, you throw it out and you put a new one, right? If it's a rechargeable battery, like your phone, you just plug it into AC current, you charge it again, and then you go ahead and you start using it. It all depends on what type of battery you have. But this is kind of what we talked about yesterday, right? We talked about what a circuit is and what we need to have a functioning circuit. We need our push to make the electrons inside of our copper, because what are we going to be using here in the class? Copper. We don't use aluminum here in the class. We only use copper. So when we apply pressure to the copper, the electrons, the free electrons inside of the copper will start moving, and then they're going to start doing work for us. They're going to create heat, they're going to create a magnetic field, and they're going to turn on lights. They're going to give us a potential for our receptacles. And when I say a potential, because I don't know what the customer is going to connect to the receptacle, right? I go and I install them in their house, I install them in their kitchen, and unless it's a specific receptacle for a refrigerator, a specific receptacle for a range, a specific receptacle for a microwave, if it's a receptacle on their countertop, I don't know what they're going to connect. They might connect a coffee maker, a toaster, a microwave. They might connect a hot, what do we call those, like the hot tops, the one that take like around 3 hours to cook, a slow cooker, right? Those. They might connect a slow cooker to it. I don't know what they're connecting, but I'm gonna leave a circuit that is gonna be efficient so that the customer doesn't have to go to the panel and start turning on the breaker because the breaker's tripping. So as an electrician, when we're designing our circuits, when we're running our circuits, we have to make sure that the customer's investment is worth it. We're not gonna leave them something that maybe we saved a couple of $100, $300, $400, but then the customer is left with a circuit that is really non-functional, right, for whatever the need that they need.
Like usually it's like an electric stove or a dryer that needs a special outlet or the.
No, the code tells us that a range, because it is, it's set in place, it's not gonna be moving because it's not easy to move your range. If you wanna clean behind the range, you sometimes have to like move the range back and forth because the space is made for 30 inches. So it's set in place. So the code tells us that because that appliance is set in place and it's not easy to move, then they need a dedicated circuit. So that circuit, that receptacle is specifically for that range. Because how easy is for you to get behind your range to put an extension? It's not easy. And it's not safe because you have heat behind that range. And putting an extension cord and running it somewhere else is not safe. So if the customer does that, and you see it, advise them not to do it. But that's why we go ahead and we put just one receptacle behind the range. And that's just something that we do because we don't want the customer to have another receptacle where they can plug into something else, you know, because they don't really understand how dangerous that can become. But those types of receptacles, you have to have a dedicated circuit. Now for the other receptacles that are around your counter, those are general use. So those are for small appliances, like the blender, the coffee maker, the toaster, or anything else that you want to connect. But there are some people that run 15 amp circuits for those kitchens. We never run 15 amps for receptacles. We always run 20 because that gives, the customer a better circuit. So if they connect the toaster, the coffee maker, and the blender, their breaker's not gonna trip, because we left them a good circuit, so that they can connect all of their small appliances. But that's up to you, because the amperage of the circuit is not really something that the code goes into in certain areas, but,